Welcome to the 7th Global Math Project webinar titled Dive Deeper into Exploding Dots. My name is Samuel Santamor. I will be the moderator for this 30 minutes webinar. Tonight we will be continuing from last session, episode 6, that was titled Learn More About Exploding Dots, Kapow! And this is really the follow-up from the last session. Just before we start, there's a few housekeeping items that I would like to go through with you, just to make sure that everything is clear and to go. If you have questions, make sure you type them in the chat box. You can see people already started entering comments. That's perfect. If you have any technical difficulties, same thing, trying to ping me there. I will remain in the background and trying to help you as well as I can. And if we run into technical difficulty, for example, if Sunil cannot hear us, or if we cannot hear Sunil, which is actually the case right now, we will play with it and figure something along the way, and hopefully Sunil will join the chat box with you guys. So now, well, to you, James, and hopefully Sunil very soon.
Wonderful. So we all set. Can people now see my live dock camera? Let's hope we're good to go then. All right, so Exploding Dots Part 2. As Sam said, kapow! I should be writing kapow all over the place. So let's make this Part 2 of the story of Exploding Dots. And just to get it briefly back in our heads where we left off last time, it was with the 10-1 machine. And if you remember, one of these machines is just a row of boxes that go as far to the left as we please. I call this a 10-1 machine. And the idea is you put in dots. Dots always go in the rightmost box. There's a dot, da 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 da. When there's 10 dots in a box, kaboom, they explode to be replaced by one dot, one place to the left. So if each of these dots is worth 1, that means this dot here is worth 10 ones, which is 10. And 10 of these, whenever that happens, will explode, kapow, to be replaced by one dot, one place to the left. So this dot here must be worth 10 tens, 100. And then 10 of these will make one of those, 1,000, and so on. So last time we discovered the 10-1 machine, and for example, the code for 273 in a 10-1 machine would be literally what I just said. 2 hundreds, there it is, 2 hundreds, 7t, t is short for 10, so 7 tens, there they are, and 3 here. So there's the code for 273, 273 in a 10-1 machine. And we speak 10-1 machine because of our humanness. If you recall, it's because of these things. We have 10 fingers, 10 digits on our hands. We naturally think as human beings, 10's a good number for counting, so we prefer in society to go with a 10-1 machine. Grand, grand, grand. And that's where we left off last time. But we knew that actually it doesn't have to be 10-1. Math could do any machine it liked. It could do a 2-1, and we discovered binary, or 3-1. We discovered ternary back then. Or we can get kind of crazy and do things like 3-2 and discover fractional bases. Very exciting. But what I want to do now is actually go back to the 10-1 machine. Let's just follow society for a few minutes and see how the arithmetic we've learned in grade school and primary school actually follows very naturally, very visually, just from this machine. And of course, what I'm doing here is actually nothing new to the world. What I've really got here is an abacus. So much of the world works with an abacus, which is basically, instead of boxes, they have rods. Instead of dots, they have beads. And whenever 10 beads slide up on a rod, they go slide them down, kapow, and raise one dot, one bead up on the rod, one rod over. So this really is an actual abacus, but I'm just drawing dots and boxes instead of rods and beads. All right, so let's look at some arithmetic. Let's go through primary school mathematics. Let's see how it all works in this beautiful visual way. For example, if I did 273 plus 112, that is a very easy problem to do. I know we can do it. 2 plus 1 is 3, 7 plus 1 is 8, 3 plus 2 is 5. Beautiful, 385. And if you watched me do that, you might have just balked at something, because I did something strange. Because I think most people naturally go right to left. And I just did left to right then, which seems awfully peculiar. But actually, if you go right to left, you'll get the same answer as me going left to right. We're fine. But I always thought it was strange as a child that in math class, I was always being taught to go right to left, when in every other class, it was left to right. Math was very strange. Well, the trouble is, of course, I've chosen a very nice problem here. If I did a harder problem like 273 plus 189, then matters become interesting. Okay, just to show how quirky I am, I'm still going to go left to right, how I was taught to read. 2 plus 1 is 3, 7 plus 8 is 15. 3 plus 9 is 12. And there's the answer, 315t 12. I even just said it correctly. 315t, ty is 10, 15 tens, and 12. And I can even draw you a picture to show you that I'm actually correct in this strange, strange way of saying it. Here's 207t3. We're being asked to add 189, so 100. There it is. 8 more tens. I can do that, no worries. And 9 more ones. Piece of cake, here they are. And look, I can actually see I do indeed have 3 hundreds. I have 15 tens and 12 ones. The answer truly is 315t 12. Great. That's actually mathematically solid. There's actually nothing mathematically wrong with that answer. It's just the society thinks it sounds strange. Mathematically, it's got my stamp of approval. All right, but the real question is, yes, 315t 12 sounds weird to society, so how could we fix up that answer for society's sake? Well, actually, you might think, well, we could do some explosions. This is a 10-1 machine after all. 10 dots do explode, become one place over. So let's do some explosions. You might want to go right to left because that's how we've been trained. Let me just be perverse and do 15 instead. Let's explode 10 for the 15. 10 explode. Kaboom! Where is it? That was 8, 9, 10. Leaving, what, 5 behind and an extra dot there. So really the answer is now 405t12. Still correct, still a bit weird. Let's do another explosion. 10 explode. Kaboom! 10 explode, leaving, what, 2 behind. Extra dot here. Now we've got 462. Beautiful. That's society's answer. In fact, that's the answer you get here. If you did the standard algorithm, go right to left, you get 3 plus 9 is 12. You don't write 12. What do you actually do? You say, okay, I'll allow myself to write the 2, but I'm going to take 10 of them. It's like an explosion. Kaboom! And put an extra dot there. So actually, when you do the standard algorithm, you really are doing the same thing as me. You're just going right to left and doing the explosions as you go along. I just have to prefer to go left to right, as I was taught to read, and do the explosions at the end. It's just a style thing. That is all is good and correct. But the funny thing is, most people don't realize that all good and correct mathematics is actually good and correct. Do whatever you like. If it's good and fine, it is then good and fine. So whatever style suits you, is go for it. Your own mathematics, let it be your own. Okay, let me carry on. So let me do something like subtraction next. So let me just whip through grade school subtraction. And you can see I'm sort of pausing here because I'm having some trouble. Because I don't actually believe subtraction exists. To me, subtraction is actually addition again, just like we've been doing before. It's actually the addition of the opposite. And the reason I'm pausing is that now means I need to develop the notion of the opposite. Now, I've been talking about dots in the last few webinars. So I now need to know what the opposite of a dot is. I need a notion of the opposite of a dot, which gives me 2 problems. 1, what shall I draw for the opposite of a dot? And 2, what shall I call the opposite of a dot? All right, so since I can't hear anyone at the moment, or I can't see what's going on in the chat box, alas, I have to make some executive decisions, I guess. Let me just draw an open dot for the opposite of a dot, and let me give it a name. I will give the name that I think every audience of children I've ever gone to in the world and talked about exploding dots with has consistently told me this is the name we should give for it. We should call the opposite of a dot a Todd. Do you see where that's coming from? Do you see what these clever kids think about? That's just the word dot backwards. I like kids. They are very imaginative, very, very, very grand. All right, so here's a dot. Here's the opposite of dot. We'll call it a Todd. And the idea is it's like matter and antimatter in science fiction. When you put them together, a dot and a Todd together, they like, I don't know, implode. They just go poof. They just annihilate, just disappear. So you get a picture that looks like, well, actually, what do I draw? I guess I just draw poof, and then it's really a picture of nothing. A dot and a Todd together make nothing. All right, so let's carry on. Oh, I see my screen is frozen. Hope your screen hasn't frozen. Are we good now? Okay, I think we're good now. All right, so let's do some subtraction. Let's do something like 343 take away 121. Great. Well, really, to me, as I said, subtraction doesn't exist. It's the addition of the opposite. So here's 343. Okay, that's grand. I think I've got that right. And please add to that 1 anti-hundred. Okay, that'll be 1 Todd in the hundreds place. Grand. Now let's add 2 anti-tens. There'll be 2 Todds in the tens place. Fine. Now let's add 1 anti-1. There'll be 1 Todd in the ones place. Great. There it is. Next question. Will there be any annihilations? Well, yeah. I see this dot and this Todd right here in this first box. That they would annihilate and go poof and disappear. In fact, you'll have two annihilations in this middle box. You see it? Two dots, two Todds. Now I'm going to get poof, poof, like that. And then one dot and one Todd in the final box, poof, as well. So that leaves me 2, 2, 2, 222. But it's just as though I went left to right again, because I love going left to right. 3 take away 1 is 2. 4 take away 2 is 2. 3 take away 1 is also 2. Bingo. Left to right. I tell you, left to right is the way to go. If we're going to teach kids to read left to right, let's have it be left to right in math class too. Though actually, you might be questioning this one. I chose a very nice example. What if I chose a more complicated example than this one? What is something like 324 take away 148? Is that a little more complicated? Is that a bit juicier? All right, let's do it. Well, I'm going to go left to right because I seem to be in that mood tonight. 3 take away 1 is 2. 2 take away 4 is -2. 4 take away 8 is -4. The answer is 200 -2t -4. And that is absolutely mathematically solid and correct. Beautiful. Whoa. Let me draw you a picture to prove to you that I'm actually right. Sounds very strange, but here goes. Here's 324. Right. I'm going to add to that 1 anti-100, 4 anti-10s, and 8 anti-1s. Whoops, going to make my Todds look like Todds. Will there be any annihilations? You bet. First box, poof. Second box, poof, poof. Last box, poof, 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 poof. There was 4 of them. And what am I left with? 2 dots in the hundreds place, 2 anti-dots in the tens place, and 4 anti-dots in the ones place. I really do have 200 -2t -4. So now the challenge is that although that's mathematically solid, mathematically correct, and I will give it my stamp of approval as a professional mathematician, it does sound weird to society. So how can we fix that answer for society's sake? Well, okay. Since I can't hear you, which is kind of sad, I'm wondering if you're guessing that you might want to do something with one of these actual dots on the leftmost position. Because that dot there really came from 10 dots on the box one place over. So we could actually unexplode it. So I need a good sound effect for unexplosions. So what's the opposite of kapow? I guess that'd be, what, whack or something? That's hard. Maybe I'll just go like slurping sound. One of these dots unexplodes, becomes 10 dots over here. Okay, that's 10. My picture's getting a bit tight. So I've got one less dot over here. So there's 1 dot in the hundreds place and an extra 10 dots in the tens place. Then there'll be some annihilations. 2 anti-dots, 2 Todds in the tens place annihilates with 2 actual dots. Poof, poof, leaving me 8. I now have the answer 180 -4. Still absolutely correct, still strange to society. So I need to fix that answer up a little bit more for society's sake, not for the math's sake, for society's sake, and I can do it with another unexplosion. Take one of these dots in the middle, unexplode, 10. 1 less dot, 7. Extra 10 dots in the ones place. Piece of cake. Some annihilations, you bet, 4 of them. Poof, 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 poof. Leaving 6 behind. 176 grand. Now, actually, the standard algorithm that goes from right to left, I'll speed through it right now, actually is this algorithm we just did here. It's really the same argument. 4 take away 8, we say we don't like -4. So what do? Well, I think school curriculum calls it borrowing. You take one of these 2 dots and make an extra 10 dots to go with that 4. That's really an unexplosion. So actually, the school algorithm, of course, is correct and good. It's just going right to left and does the unexplosions as you go along. I just have to go be quirky and go left to right and do the unexplosions at the end. Again, a style thing. All good, correct mathematics is fine and correct. But I will say something. I do kind of like my left to right method here because I actually can see the answer for my quirky answer, 200 and -2t -4. Because that first 2 is really 200. That next -2 is really -20. And that final -4 is really just -4. So I've got 200, -20 and -4 Can you see that really is 176? It's actually my left to right method here I kind of like, because you actually just see the answer is correct, 176 in the end. So you just write it down left to right and just, do a quick little bit of computation and you're done. It's all a style thing, whatever suits you is good. Let me just do a quick piece of division. And the reason I'm going to do this, because actually when I finish with this example of division, we're basically done with high school algebra for polynomials. So bear with me. This is going to be 11th grade algebra in disguise. This is why I taught exploding dots in the way I've done it last session and this session with my seniors in high school. We talked about 2-1 machines, 3-1 machines, 10-1 machines. We went through addition. We went through subtraction. We also went through division. I'm going to do a division problem right now, which is basically high school algebra, even though I was taught it in grade 5. Now, here's a very lousy, horrible way I could do 276 divided by 12. It'll be correct. It'll be awfully tedious. I could draw a picture of 276 dots. Probably take me an hour. Okay, let's pretend that's 276. And the question in division is 276 divided by 12. How many groups of 12 can I find in a picture of 276? All right, there's a picture of 276. I've got one, all these dots. All I have to do is find groups of 12. There's a group of 12. There's another group of 12. There's another group of 12, and so on. And in the end, I'll get all these groups of 12, and I'll get a count of them, and whatever that count is my answer to the division problem. Great. All right, that's very unsophisticated. There's nothing wrong with that answer. It's just that approach is just awfully tedious. So let me do a more sophisticated version of this picture approach. Let me draw a more sophisticated picture of 276. I'll draw it in a 10-1 machine. Okay, here it is. 200s. And 7 10s, and 6. Great, there's a sophisticated picture of 276. 12, what does 12 look like in a 10-1 machine? Well, it's actually going to be, what, 1 dot and 2 dots. Okay, I'm going to go a bit fast with you guys, because there's a little bit of subtlety about to go on. Technically, I've not drawn 12 dots right now. To really draw 12 dots, I have to do something like this, literally draw 12 dots. And look for 12 dots in my picture of 276. But we know 10 of those are going to explode and spill over to make 1 dot to the left. 1 dot next to 2 dots. That's what I drew here. So let me just point out, the 12 dots really were in the rightmost part of the picture, rightmost part of the double box. That's where the 12 dots really are, on the right. So we're going to keep that in mind. All right, so the question is, here's a picture of 276. Here's a picture of 12. How many 12s can I find in that picture of 276? That is, how many 1 dots next to 2 dots can I see in this picture at the top? Well, can you see any? Yeah, actually, I can see lots of them. For example, there is one dot next to 2 dots. Now, to be very clear, here's the subtle point, and when I'm working with kids, I'm going much slower than I'm going right now with you. But here's a loop of dots. All 12 dots are really right here at this level, in the right part of the loop. There must have been 12 there. 10 exploded, spill over to the left. So all the dots are really on the right part of the loop. So we've got 1 at the 10s level. Okay, any more 12s? Yeah, here's another 1 dot next to 2 dots right here. Again, at the 10s level. All 12 dots are technically in the right part of that loop. Any more? Not right where I am now, but if I shift my attention over, there's another 1 dot next to 2 dots right there. Right, at the 1s level. And again at the 1s level, 1 dot next to 2 dots. Another one at the 1s level. And again at the 1s level. Wow, this is fun. 1 dot next to 2 dots. So what have we done? We found 2 groups of 12 at the 10s level and 3 groups of 12 at the 1s level. And so the answer must be 23 groups of 12. And that is indeed the correct answer to the division problem. So actually, believe it or not, this picture is the standard algorithm in disguise. I personally very much like this picture because I feel like I understand this picture. I own this picture. I can actually see what's going on. I can actually see 23 groups of 12 in that picture of 276. Brilliant. In fact, let me just show you how potent this pictorial approach to division is by doing a more complicated example. Suppose we did say 31829 divided by 102. All right. Again, this is a speed seminar tonight, just get a sense of what's out there. Of course, you can go to my website, g'daymath.org, look at the exploding dots and go through all this very slowly. And when Scurlop has that web app very soon to be released, it goes through it all there too. So all good stuff is happening. Okay, but for speed play right now, let me draw a picture of 31,829. 3, 1, 8, 2, 9. 9, there we go. Hardest part's actually counting. 102. Be careful, what does that look like? Well, it's going to be 1 dot, no dots, 2 dots, 102. And just be very clear, all 102 dots, if I did all the unexplosions, are really sitting in the right part of that little sub-picture. So the question is, how many 102s do we see in that picture of 31829? We're looking for 1 blank 2. Do you see any 1 blank 2s? Well, I do. There's one right there. 1 blank 2. Where are all 102 dots technically in that green, orange loop? They must have come from being a lot of unexplosions going on, explosions. They must all be there at the right part of that loop. That's really an example of 102 at the hundreds level. Any other 102s? Yeah, I see one right here. 1 blank 2. My loop's getting a bit messy. Will you let me get away with this? Can I just do 1 blank 2 like that? Can I do a split loop? Yeah, of course I can. Ooh, that's it for that level. Any more? Oh yeah, here's a 1 blank and a 2. Maybe I can do that. Another one at the tens level. Any more? Oh, here's a 1 blank 2. The ones level. Another one there. 1 blank 2. And that seems to be it, which is annoying because I've got all these dots down here still sitting there wanting what to do themselves. So how do I read that answer? Well, okay, well, clearly the answer is 312. We've got 3 at the hundreds level, 1 at the tens level, and 2 at the tens level. So the answer is 312, and we've got these 5 dots just sitting there wanting what to do with themselves. Well, depending on what grade level you're in, you might just say 312 with a remainder of 5 dots. There's the actual remainder. You see it. If you want to be a little more technical about the mathematics here, you can say plus it's 5 dots still waiting to be divided by 102. So there's the actual mathy answer for preciseness. 312 and 502. Wow. Division, piece of cake. All right, now let's do the high school. Why was I doing this with high school seniors? It's because of this very moment right now. The point is, mathematics does not care about us being human. It doesn't care about the fact we're born with 10 fingers. It doesn't need us to be doing this in a 10-1 machine. We can do this in any machine we like. We can do it in a 2-1 machine, the math will be fine. We can do it in a 7-1 machine, the math will be fine. So what I'm going to do now is repeat what I just did today in all machines all at once, which sounds crazy. How am I going to do that? I'm going to do it as follows. I will draw you a machine. But I'm going to be coy about this machine. I'm not going to tell you what machine I'm thinking about. It could be a 10-1 machine. I'm just not going to tell you. It could be a 2-1. You won't know because it's in my head. I'm just not telling. It's the mood I'm in. You don't know what machine this is. But you do know, at the very least, the dots here in that first box are always worth 1. Oh, at the most glorious punchline. Okay, here we go. So I'm not quite sure where we left off. We're just doing grade 5, grade 6 long division. We just did problems like 276 divided by 12. Beautiful. There it is in a 10-1 machine. The point I was making about why graduates even, why was I going through this whole story that seemed like primary school, grade school mathematics, is because my point is the math does not care about it being a 10-1 machine. Math does not care about us being humans with 10 fingers on our hands. Math can do this in any machine. So I'm now going to literally do it in any machine. Just to give a nod to algebra classes all across this planet, there seems to be a favorite letter of the alphabet. If you don't know what a number is, that letter is X. So let's call this X machine. If you don't know what X is, now I am personally thinking of a number in my brain, just not telling you what I have in my head for it. There is some number, but you do know if it's an X1 machine, it'd be like for tens, it'd be 1, 10, 10 squared, 10 cubed, so on. Or for a 2-1 machine, it'd be 1, 2, 4, 8, 16, so on. But any machine is going to be the powers of the number you're dealing with, in which case, for an X1 machine, we'll be dealing with 1s, X's, X squareds, X cubes, and so on. X1s makes X, XX's makes X squared, XX squareds makes an X cubed, bingo. So, without any fuss, without any thinking, we've just been in grade 5. I'm going to suddenly ask this high school algebra problem. What is 2x squared plus 7x plus 6 divided by x plus 2? But you know what? I'll tell you, I've actually done this with 5th graders, and it's not an issue because, well, it does look visually scary. I do give you that. Is, mathematics, be human about it. If it looks scary, it's okay to be scared. Have a deep breath. But we can do it. Look at this. 2x squared, 7x's, 6 ones. Bingo. I believe I've just drawn 2x squared plus 7x plus 6. There it is in that picture. And we're looking for in that picture for x plus 2. And what would that look like? Well, if I draw a little sub picture on the side, it'll be 1 dot for 1x and 2 dots for 2 1s. So the question is, can you see in the picture of that big complicated expression on top any 1 dots next to 2 dots? And of course, the answer is yes. For example, there is 1 dot next to 2 dot, right at that level. And below it, there's another one, 1 dot next to 2 dots. Well, yes, not at that level, but over to the next spot over, there's one. And there's another one, right here. And there's a third one. My loop's getting a bit strange, but there it is, 1 dot next to 2 dots. So I've actually got 3 at the 1's level and 2 at the x level. Bingo. The answer must then be 2 at the x level, 2x, plus 3 at the 1's level, 3. 2x plus 3. Wow. There it is, high school algebra, done, just like that. In fact, I don't know if that felt like deja vu, because that is exactly the same picture. In fact, can I put these two pictures together? Can you see that this grade 5 long division problem is actually identical to this high school algebra polynomial division problem? Well, of course it is, because actually, if I did reveal to you x really was 10 in my brain all along, what have we just done? Well, if x is actually 10, 2x squared plus 7x plus 6 would actually be 210 squared, 200, plus 710, 76. 276 divided by 10 plus 2, 12, would have to be 2x plus 3, 23. Indeed it is, because 276 divided by 12 does indeed equal 23. We just did it previously. This is what I love about exploding dots as a high school teacher, because there it is, that polynomial work just falls into place. We visually own it. It's a piece of cake. It's beautiful. In fact, just to show what a piece of cake it is, let's end off with one truly, truly nasty looking problem. And we'll see how brilliantly easy it actually is, just by drawing a picture. Let's do x to the 4th plus 2x cubed plus 4x squared plus 6x plus 3, all divided by x squared plus 3. Now, actually, in some high school curricula, this would be considered too hard a problem, because I'm dividing by a quadratic this time. Now, in college classes, when I was a university professor, we had to do this sort of thing all the time, divide polynomials of high degrees by each other, so this actually could be considered college mathematics. Anyway, doesn't matter. It's a piece of cake. Just draw a picture. You'll see what I mean. It'll probably take us longer to draw the picture than it will to actually problem. Okay, here's some boxes. 1x to the 4th, and 2x cubes, and 4x squareds, and 6x's, and 3. There it is. That's the numerator. To be divided by x squared plus 3, that would be what? 1x squared, no x's, and 3 1s. So we're looking for 1 blank 3. And do we see any? Of course we do. Here is a 1 blank 3. Now, I went fast with you guys, but if I could do all the unexplosions, I know all the dots are really sitting there at that level. Any other 1 blank 3s? Why, yes. Maybe I'll change colors to make it a little more clear what's going on. Here's a 1 blank 3. If I could do all the unexplosions, they're all sitting down at that level. And there's another one right there, actually. 1 blank 3. Also at that level. And there's one more. Next level down. 1 blank 3. I can now see the answer is x squared plus 2x plus 1. x squared plus 2x plus 1 in my messy sheet work here. Beautiful. Polynomial division, piece of cake. Now, I'm going to be a bit of a tease. There is actually a serious problem with this technique. And, you know, I'm going to see if you can try to figure something out. Because I've been pulling the wool over your eyes a little bit. So I'm going to leave off today's seminar with a challenge. What would you do with this one? X cubed minus 3x plus 2 divided by x plus 2. I've been carefully avoiding TODs. You can draw a picture. It look like an x cubed. There it is. No x squareds. 3 anti-x's, so 3 TODs and 2 1s. And I'm looking for x plus 2, which we've seen before be 1 dot and 2 dots. And right now, it looks like we have no hope. This looks impossible. There is no 1 dot next to 2 dots in that picture. And I'll tell you, it's actually right now, this is the absolute reason I really enjoyed being a high school teacher, because we have a problem and we feel that we have to be compelled to want to solve it. Kids don't believe me that I'm saying it's impossible. They feel it has to be possible. And what I love about it, they have the tenacity, they have the grit, and they make it work. They find a way to push through this and solve this problem and figure out a way to make this work. It's actually delightful, brilliant, human, and intensely joyful. Who knew that dividing polynomials would be a source of great joy? Okay, I love being a high school teacher. That's it. I will absolutely teach polynomial division, not because I think we need to know how to divide polynomials in life. In fact, we really don't. But if it can be a gateway to joy and meaning and relevance and absolute, uplift to our human minds, then we absolutely do it. It's like poetry, it's like music, it's mathematics. So I'm going to stop there. I invite you to try to figure out a way to make this method work, to prove that I'm a liar, that it can be done. There's a way to make it happen. I invite you to go for it and have great fun with it. And if you get stuck, of course, everything is on my website, so I talk about it there. So don't feel bad. Feel free to look at it there if you like. That's fine too. All good ways to enjoy mathematics are good ways to enjoy mathematics. So I'll stop there. So thanks very much.
Thank you, James. That was amazing and a perfect follow-up to the last session. By the way, I wanted to mention that these webinars are recorded and we post them on the Go Math Project's YouTube channel, and you can watch them directly on the channel. We try to share them on social media to make sure you guys know about them. But they're there for you. They're available, free to stream or download someplace probably. And then just before we leave, James and Sunil, if you are still there, if you can hear us, I just wanted to make sure that, again, you guys share how people can reach out to you, social media, email if you want.
Excellent. Am I still screen sharing?
Yes, you are.
All right. I am on Twitter at James Tanton. So if you know my name, you know how to find me. And the place to really learn about exploding dots and take part in Global Math Week is explodingdots.org. And if you go to the frequently asked questions there, you'll see things like, how can I learn more about exploding dots? And that will take you to the website I mentioned earlier. Or what is this thing called Global Math Week? How can I get involved? It's a global phenomenon. Don't miss out. Be part of it. We actually have, at this point, which is almost at 500,000 students from 101 different countries and territories signed up to take part in Global Math Week. We're right at that brink. Maybe you want to register and sign up and do some exploding dots for students too in October and take us to that 500,000 mark. Actually, we want to go for 1 million. Let's go for 1 million kids. So don't miss out. Be part of the Global Math Week. Be part of the global phenomenon.
Registrations are going really crazy. I keep an eye on them. And it's really, really interesting. You can feel the interest is really like constantly gaining and going faster. It's really nice.
Absolutely.
I also want to make sure that we share Sunil's Twitter handle, because I'm sure you will love to hear from you guys. And yes, at Math Garden, I've also put it in the chat box to make sure. We have at Global Math Proj on Twitter.
Oh yeah.
Let's not forget this one.
It's a little unfortunate. The ACT got missed, but you know, they only let Twitter only lets you have a certain number of characters in your names.
So long, so long, right? Twitter, more than what, 10 characters, 12 characters? Anywho, I also wanted to share BuzzMat's Twitter handle. So I just wanted to just give one quick word. We will release the online experience to everyone really soon. Some of you in the audience already saw a beta version, and we're working really hard. So excited to release that. We're so close. So guys, please keep an eye. We will try to reach out to you and let you know as soon as it's available. I'm pretty sure you will love the experience. I do.
It'll blow your mind. Kapow!
Yeah, there you go. So of course, always talk to us on Twitter, online, social media. It's always a joy to hear from you guys, get your feedback. So thank you again very much for being there. It was a bit longer. Sorry for a little technical issue, but I think that was fun, even that. So there you go. Thank you, James.
Fabulous. Thank you. Thanks, everyone. Guys.